Thank you, thank you. So I'm Sergey, I'm head of development of Blender, and today I would like to give a deep dive into architecture of our path tracing render engine called Cycles. But before that, on behalf of the entire Blender team, I would like to happily present you Blender 5.0, which was released yesterday, despite of all the Cloudflare outages. It was completely fun experience while a lot of us are here, and like some people are sick, and people trying to ship the Blender. It has a lot of new features, has a bit of breaking changes. The full release notes, you can scan the QR code or just go to blender.org and check it out. It's pretty exciting. Anyway, to the more regular scheduled program. So in today's talk, I will cover a bit of introduction what Cycles is, what's its main differences from more real-time render engine, which you're more familiar with. We'll cover the way how we structure the kernel, which is exactly the same kernel on all the supported compute backends. And we'll give a bit more detailed dive into the way how we do shading and a few other interesting things for the context of this conference. There is, of course, like much more things we can talk about for Cycles, but then we'll be here like for probably a week or something. So anyway, we have a lot of ground to cover, so without any further ado, let's jump into it. So what is Cycles? So it's our physically based path tracer for which we aim to be used for the production rendering. It's developed by the Blender project, so it's completely free and open source. And in fact, we license Cycles as Apache 2 license to allow it to be integrated in other software. We aim Cycles to be as easy to be used by artists as possible, while also supporting a lot of production features. And it uses a physically based shading system, but we don't aim to make Cycles physically accurate per se. And one of the design goals when it comes to designing Cycles, it comes back to the handling large scenes and complex light interactions and shading materials. Cycles supports a lot of features, like one of them which is less user-facing, but which is interesting for today's conference, is that it has unified kernel, which runs on CPU on all the major GPU vendors as per today. It supports cross-platform execution, and it supports multiple devices, execution on multiple devices, including heterogeneous environment. You can even do CPU plus GPU rendering, or you can mix GPUs from different vendors. It supports a lot of compositing features, mainly render layers, render passes, all sorts of jazz. Integrates with denoising algorithms, with all those custom camera lens models and things like that. Shading system is node-based. It's mainly OpenPBR compatible. There is still some differences which we're working on eliminating. And additionally, we also have the backend for open shading language. And of course, when it comes to light, it's full global illumination with the light portals, light and shadow linking, all sorts of tricks. And of course, there is much more features. Slide is not big enough to cover all of them. So what's the main difference of Cycles from more real-time render engines? Like, first of all, it's path tracing, which means it probably takes a long time to converge to noise-free image. But then at the same time, it allows for simulating quite complex light interaction or complex shading interaction. Another big difference is Cycles implements what we call shading virtual machine, which we will cover in more details later in this talk, but it's basically some bytecode machine which interprets your shading graphs. Kernel is written in C++, and we also aim to keep the feature set and the image quality and image look the same regardless of what compute backend you use, if it's CPU or GPU, or do you sprinkle some hardware ray tracing as well. We want basically be transparent for user, like what device you use without changing the final look of the frame. So how did we achieve that? So let's dig a little bit into architecture itself. So on this slide, you can see the main modules which Cycles is composed of and the relation between those modules. So let's dig into a bit more details about what happens in each of these modules. And let's start with the host application, or mainly host application adapter, whose main goal is to convert data structure from Blender representation, any DCC representation, to a cycles scene graph. It's the responsibility of this layer to take care about keeping track of what changed on the DCC side and only synchronized changes only synchronized changes. So for example, if only like one object in your scene changed and others stayed unchanged compared from the previous synchronization step, that's where it should happen. So we have obviously adapter from Blender data structure, which is maintained by the foundation, but there are a couple of the external integration for the Rhino 3D and Cinema 4D, and maybe others which are maintained somewhere externally. And we also have simple adapter from XML files, which basically loads data as is from and into the cycles directly, which is quite helpful for debugging purposes, especially if you use cycles standalone repository and don't compile the entirety of the Blender. So the next module is the session. It's basically the root object, which is created by the host application, and it owns entirety of the information needed for the rendering. For example, it owns the device abstraction object. It owns the display and write drivers. Those drivers take care of visualizing render buffers on the screen or writing them to the file. It also kind of indirectly stores the scene graph via the scene, and it also owns the render buffers, as well as providing algorithms for top-level render scheduling. We'll talk about the scheduling in just a bit. Next level is the integrator. Integrator is basically implements the host side integrator algorithms, and it takes care about the scheduling kernels in proper order, maintaining the wavefront for the wavefront renderer. And it balances work between multiple devices, takes care about adaptive stopping for adaptive sampling, and it also provides access to the render buffers, because it might not be trivial, especially when you use the adaptive sampling, where some pixels might have more samples stored in them than other pixels. The scene module is basically the storage of the entirety of the scene, including geometries, lights, shading networks, and it's stored as scene graph, where everything is a node. So geometry is a node, object is a node, nodes in the shading graph are the nodes, and I forgot if the links between the nodes in the shading graph are the node or not, but kind of would be fun if it was. So yeah, this is where like all the data which needs to be rendered is stored. We also have the module for the integration with bounding volume hierarchies. This is basically the ray tracing optimization structure, and we support a number of different BVH types. For the CPU and Intel GPU rendering, we use Imbri, we use optics for NVIDIA, HipRT for AMD, MetalRT for Metal, but we also have more naive BVH2 implementation for GPUs where there is no hardware ray tracing implemented, or for the CPUs which are not officially supported by the Blender. So officially only support x64 and ARM64, but you can compile cycles on pretty much any architecture, and on those architectures you'll use the more naive BVH2 implementation. And a bit looking like fast forward into some other parts of the presentation, that's also the module which takes care about of the refitting BVH nodes on updates. And last but not least, there is abstraction from the compute backends, which we call device. Basic idea what happens here is we make it so that all those compute backends are kind of seen in the similar IPA from the scene and integrator perspective for memory management and scheduling kernels. And we have the device abstraction implemented for the CPU. We have the abstraction implemented for all the major compute backends like CUDA, optics, HIP, Metal, OneAPI. And there's also specialized device abstraction, which we call multi-device, which basically takes care of scheduling kernels on multiple devices. So it kind of wraps around on top of the GPU-specific backends. So when it comes to rendering which happens on the session level. It's the top-level render loop, where we basically split image into big tiles, which by default they are 2 by 2K. We allocate and zero out render buffers, then enter the render loop, where we say, hey, please render a number of samples. After that, the rebalancing between devices will happen. If you have multiple device rendering, all this adaptive stopping criteria will be applied and propagated to neighboring pixels to avoid artifacts when we need to put some more work to one pixel. If needed, some render buffer post-processing will be applied. On top of that, denoising will be applied as well, and then display texture on the GPU side will be updated so it can be displayed on either viewport or in the render window. Nothing really special, because a lot of stuff actually happens in the kernel. So let's dig into the kernel side. So as I mentioned before, we have the single source in the kernel, which we compile to all the supported backends. There is, of course, a bit of the hardware or backend-specific logic implemented, especially for the hardware ray tracing. There is no easy way that we found how we can kind of mitigate the differences between backends, so that's kind of integrated for a specific backend, its own source code, but we use like some utility function, of course. And the texture sampling is also a bit different on different devices. So we have different entry points to the CPU and GPU kernels, but those entry points are basically tiny wrappers where it's like, okay, something is backend specific, and then as quickly as possible we call the actual integrator microkernel with all the data which it needs to, and then that's where all the logic will happen. And another point which is quite interesting is all the GPU backends use the same source code, which defines entry points for all the backends. There is quite a bit of preprocessor magic going on to mitigate the differences between how different backends expect things to be defined, but overall it doesn't look that verbose at all. For the language, so we use basically a subset between C++17, CUDA, and HIP. There is no magic bullet how you can automatically say, hey, can you use this feature or not, because there is no tooling for that, although having CI/CD definitely helps when you add some new feature or like work on some piece of code, and then you can ask CI/CD to test, hey, does it compile on all the backends? And as I mentioned before, we use quite a bit of preprocessor magic to mitigate differences between different compute backends. So for example, we have macros for memory qualifier, like CCL global or CCL local, where a bit of interesting piece of lore is CCL stands either to cycles or cycles compute language. Well, choose whichever you want. Other restriction is that there is no recursive function. You cannot use virtual functions. You cannot have virtual functions in a class. You cannot do dynamic memory allocations. And you cannot use double precision floating point values, just because the performance on consumer-rated GPUs are not very great. And we also implement a number of utility functions to make the same code compile on different backends as well. So for the vector types, we basically stick what CUDA uses, like float 2, 3, 4, works as expected. Similar thing exists for integer, unsigned integer, unsigned char buffers. There are, of course, mathematical operations and some functions implemented to support compilation of same code on all the backends. A bit of a difference, which by now it's a bit of the legacy from our OpenCL days. To create the vectors, there is a dedicated function, make float2, for example. And to further make things more consistent, there is like a lot of operators implemented, especially on the CPU, on some functions on the CPU. When it comes to how data is accessed from the kernels, so the small constant data is stored in basically in a constant memory, and it's stored in what we call kernel data. It's basically a global variable which is accessible from everywhere, and that's where things like integrator settings are stored, or the film settings, things like that. Large read-only data is stored in global memory or texture handles. In the code, you probably will see, hey, why something is called texture where now it's not texture at all? Well, it's a bit of legacy, which we didn't clean up from everywhere yet, because back in the days, texture was the only way how to access things quickly. On a CPU, to keep performance good, we utilize CPU SMID intrinsics, so we use intrinsics quite extensively. But we also have the naive fallback to the Scalar implementation to support CPUs where we don't target officially. So for us, historically, we used SSE and AVX intrinsics. So that's what you can see in all over the utility functions. To support ARM64, we used SSE2 Neon header, which works pretty well. It basically translates SSE or AVX calls to Neon calls. There's a bit of caveats that some of the intrinsics cannot be cheaply represented by ARM Neon, and there's quite some overhead to them, and it could happen in a hot code path. Unfortunately, there is no magic solution to find those cases, so it's kind of like you need to carefully look at the code or on a profiler and replace those intrinsic with ARM Neon, like direct usage of ARM Neon intrinsics. So when it comes to implementing the actual kernel logic, one of the most naive and most simple to understand approaches is what's called Megakernel. It's where the path is being simulated from its beginning to the very end, where it basically starts from generating the camera array, then goes through all the bounces by finding next intersect, doing shading, doing emission accumulation, things like that. So while it's very simple to implement and it works quite okay for very basic render engine, it's not friendly to the GPU at all. But turns out it's one of the most efficient ways to implement path tracing on a CPU, at least until you use what seemed to do shading on multiple points at the same time, or until you use array buckets, or like array. Well, basically, until you wanted to find intersection of multiple arrays with the scene at the same time, which we currently don't, but that might change in the future. So this is a simplified example of the megakernel, where it's like, okay, it's just like one function, and you call certain amount of things in order. Basically, what we're trying to do in cycles is we implement megakernel approach, but by calling the microkernels in a specific order. There's a bit more complication in the actual megakernel code, because it kind of needs to mimic a bit of the wavefront approach, but all boils down of calling kernels in this order, basically. So for scheduling, it's basically we do parallel for across the pixels, and each of the pixel we render a number of samples. It might not be the most efficient way where you have like some very hot pixel, but it doesn't really happen that often in practice, where like one pixel is so much hotter than the others. And yeah, again, like we just call the microkernels as quickly as possible from this megakernel. Alternative approach is what is called wavefront approach, and we basically implemented a wavefront approach in the cycles based on a couple of papers. One of them is Megakernel Considered Harmful, and the Array Light Transport paper. They go deeply into details explaining why exactly things quite bad on a GPU, but basically what the wavefront approach is solving is the cache coherency problem, where some of the threads in one warp on a GPU might be doing array intersect, some other threads might want to do shading, others might want to do light sampling, and GPU ends up like masking like a lot of threads, and then the utilization of the threads is not very good. So the way wavefront approach solves this problem is by introducing microkernels. So you have a kernel for scene intersect, you have kernel for the surface shading, you have kernel for volume shading, and so on and so forth, which intrinsically minimizes the possible discrepancy between threads. And another point which this approach helps is it helps tremendously compilers, because all the kernel is much smaller, than compiler might make better guess about the register spills and amount of registers it needs to allocate and further improve the performance, even if the compiler is not yet mature enough. So this is typical scheduling graph. It's a bit hard to visualize what exactly is happening, but basically the idea is that everything starts with the generating camera rays. Then if there are any volumes in the scene, we will initialize the volume stack to know which of the volumes are enclosing the camera, so then we can do proper volume integration. And then we enter the classical Megakernel loop where we do scene intersect, and then we either go to the sheet background if we didn't hit anything, or we go to the sheet surface if we hit something, and based from there we go either into SSS rendering or into some more tricky parts for the shadow linking, things like that, and at some point loop closes. So the question is, how do we pass data between the kernels? And for that we have what it's called integrator state. It's basically one big array of state for each of the paths, and this state basically includes all the data which needs to be passed between kernels to properly integrate that path from the beginning to the end. We allocate millions of those path state elements, so then we can have multiple, a lot of paths in flight, so the GPU is happily and busy, but which adds the requirement that the state needs to be as small as possible. And state might be either inactive if the array terminated, for example, hit the world, or it could be active, and if the path is active, then the state will say, hey, which kernel it wants to execute next. And to access the state, we use some of the macros logic to do either read or write to it. And the reason we needed to do it is because we actually use different layout on a CPU and a GPU. While on a CPU, we follow more traditional array of structures approach. On a GPU, we implement structure of array approach, which usually ends up in a better memory access patterns. There is a bit of exceptions when your kernel needs to read the entirety of the structure. For example, the entirety array intersect, where you have little UV and maybe object ID. For those cases, it turned out to be more efficient to store data as array of structures. So overall, it kind of becomes the structure of array of structures, which is quite fun. And to mitigate the difference between CPU and GPU, which is different layout, it's kind of code generated using quite some of the preprocessor magic. But it all happens in one path. So I think some other render engines use the external Python script parser to generate this state, but for us it's just the preprocessor magic to either generate structure of array or array of structures. So for scheduling the wavefront, it's also not very complicated. Basic idea is that, okay, so we allocate all the integrator states, we mark all of them as inactive, and then for each of the big image tiles, we generate what's called work tiles, which are much, much smaller, maybe 16 by 16, with number of samples to be rendered. And while there are still those work tiles to be rendered, we enter the loop, and we check, hey, are there enough space in the wavefront to fit more work tiles to generate more work for the GPU? If there is, then we will collect the next work tiles to be rendered, and then we will compactify the existing states so that all the active states are residing somewhere in the beginning of the array, and then we just execute the init from camera kernel to fill in the rest of the available space. Now, once that is done, we check which is the most requested kernel, and then we basically execute that most requested kernel, hoping that that's the kernel allow us to free up the most space in the integrator state, or the one which will keep the GPU the most occupied. There is a couple of caveats to keep in mind before scheduling more kernels, is that some of the kernels might branch off into shadow ray. For example, the surface shading might branch off to the shadow ray, which means it might need extra space in the state. Or if you use shadow catcher, which we implement as basically differential rendering, it might branch off into the secondary state, and each of those mine and the shadow catcher state might also branch off into the shadow ray. So we keep an eye like when we schedule those kernels, and only do it when there is enough space in the main state array, just based on quite pessimistic approach, saying, hey, maybe everything will be branching off. So the way we distribute Blender, and well, we don't distribute really cycles, it comes with Blender. So the way we distribute cycles is we actually prefer to precompile GPU kernels for all the active GPU architectures, which we do for CUDA, HIP, HIPRT, and one API. So it's like quite a few kernels we ship. For the optics hardware ray tracing, we ship PTX, which does require one-time optimization of client machine. For the metal, unfortunately, it's always just in time. So we also ship the code so the metal can compile it. So the goal with all of this is to allow artists to have the pixels on the screen as quickly as possible, even when they have the brand new Blender. They open their beautiful scene, they hit F12, and then see immediately pixels on the screen, and they're like, wow. So to minimize the amount of space in the release distribution, we use the STD compression for those kernels, which is quite a lot of time, quite a lot of space. Now, when it comes to GPUs which are not yet mainstream, so to speak, so we do work with some of the vendors to expand GPU support in cycles. But for us, adding extra compute backends ended up to be quite a burden, so we really prefer not to add yet another backend. And what we're pushing everybody is to hook up to our existing one API backend, which basically utilizes SQL standard via DP C++ compiler. And hopefully we can all agree on that, but we'll see where that goes. So another interesting topic is how do we do shading in cycles? So as I mentioned, there are two shading systems supported by cycles. One of them is more native to the cycles, which we call shader virtual machine. It's supported on all the compute backends. And we also support open shading language, which is currently only supported on a CPU and optics, with some of the performance downsides, especially on optics, which we would like to work on, but so far it's a bit hard to prioritize. Regardless of the choice of the shading backend, cycles will do some preprocessing on the graph level. So for example, it will remove the unused nodes, or will remove the dead branches. It will do constant folding of some nodes where it can. It will do node deduplication. So for example, if you sample some volume grid and the same volume grid from multiple nodes within your graph, it will say, well, that's kind of inefficient, so let's convert everything to one node. And even though on OSL we'll do a similar thing when we ask it to compile the source, doing it ahead of the time, as graph operation actually saves quite some time, because then compiler doesn't need to think so much, but we're not going to focus on OSL in this talk. Instead, we'll talk about the shader virtual machine. So what this shader virtual machine is. So the interactivity in cycle is one of the key points which we want to achieve. We want artists to be able to tweak their node graphs, the parameters in the shading, and have as instant response in the viewport as possible. And compiling specialized kernels could be time-consuming. It will inevitably lead to hiccups or to even stutters in the interface, depending on the backend. So what we do instead is Cycles basically compiles the shader graphs into bytecode, in its own bytecode, which it knows how to interpret and implements an interpreter for this bytecode, which means there is no need to any external SDK, there is no need to pull yet another LLVM version to do just-in-time compilation, there is none of that. And another point is the implementation of the SVM is exactly the same on all the backends, and the same kernel can interpret whatever shading graph you're trying to shade. So it's not like you need to do any of the shader-specific SVM kernels. So how exactly does it do? So basically, Cycles generates this bytecode and stores it as elements of Win4 elements. It's doing it by traversing the shading graph in DFS order and compiling nodes for which it knows all the inputs. Each of the shading graph nodes can be compiled to either one or multiple Win elements. One is the minimum because that's where your opcode is stored, and it leaves you spaces for 3 32-bit elements where you can pack some parameters for that node to operate with. It could either be integer or float or like any bit-packed parameters. If this is not enough for some nodes, like principal BSDF node can say, hey, I wanted to allocate a bit more of the Win4 elements to store my parameters. There is basically essentially SVM memory, which we, for historical reason, call stack, because of it was filled in from the early days of the implementation, where nodes can read values from or they can write values to. And yeah, for the evaluation, it's basically SVM traverses this array of elements in order, and essentially it's just a big switch statement for the possible opcodes, which runs in a loop. So compilers have a lot of fun compiling this SVM. Some compilers are having so much fun that even the explicit force in line, force no in line doesn't really help, but we are kind of like now in the quite good state with all the compilers where they do quite decent decisions for the spilling and register usage. So here is like a bit of an example of how this SVM compilation works. So there is very simple node graph where there is diffuse BSDF, which is textured and use whatever Fresnel node to drive its roughness. And I didn't notice that by default we use IOR of 1, so it's like very useful setup. So what it does to compile this node tree is we actually start with the material output and we generate the jump table for this material because we can support either shading, surface shader or volume shader or displacement shader. So that's where essentially we store offsets in this bytecode where each of the parts of the material begins. In the beginning, we don't know offsets yet, so we just write the opcode and we'll be coming back to this node once the compilation is finished. Then we go in DFS manner and find that, hey, there is an image texture node, for example, with a bit of the caveat that it has the vector input that is basically position at which the sampling needs to happen, and each of the unconnected sockets is actually becomes implicit node of the specific types. In this case, it's attribute node for the standard UV position. So we write bytecode and into the SVM bytecode, and then we allocate space in the stack to store the result of the attribute. Then we can compile the image texture itself, which again compiles to a number of bytecodes where essentially we say it's opcode of texture image. It writes and stores things from specific offsets, and it also packs like all the parameters from the node itself into the unused elements of the Win4. And then similar thing happens for the IOR, where we say, well, IOR needs scalar input, which actually compiles to the set value node opcode with that specific address, and it basically writes 1 there. Similar thing happens for the normal. We basically read the geometrical normal attribute, also write it, and then compile the Fresnel node itself, which reads values from the stack and writes the resulted Fresnel term into the stack. And Then we start compiling BSDF node, but it also has unconnected normal node, but we already compiled that node, so it kind of reuses the same result of previous calculation of that node, so we don't do anything. And then we compile the BSDF node itself, which during interpretation of this node, it will actually generate closure for the integrator to be used in the kernel. And a couple of things which happens after this stage is we go back to the jump table, to the jump node, and fix up any offset which we need. And we also actually write the end opcode, so then SVM knows where to end, but we run out of space on the slide, I suppose. So that's just an example of how compilation happens, and then at the runtime, this array being interpreted from left to right, basically, and do what the opcode is supposed to do. So the benefits of this approach is that we are achieving the minimal and predictable time until the first pixel on the screen. So it's like minimal time, and it's also non-blocking tweaking of the parameters. The downsides is that it does stress GPU compilers a lot, so sometimes you do need to give a help to the compiler to not spill too much. Its performance probably less than compile specialized shader graph. And it's also because we have limited size in the SVM stack or SVM memory. It also has a limitation how complex your material shader graph could be. If you have like a lot of non-tree looking structure that you can run out of SVM memory. Looking forward, we actually investigating whether this approach can be used in our real-time engine, which we call Eevee, just to exactly minimize the stuttering and the wait time when artists tweak materials. And another point is we are looking into supporting material X natively in cycles. And one of the easiest way to do it is to go via OSL, but then you kind of hit the same problem that, hey, now you need to be compiling something, and while something is compiling, maybe we will do like this two-stage optimization, material optimization, similar in both Eevee and cycles. We don't know yet. It's something we are currently looking into, not necessarily as the highest priority. So let's talk about texture filtering, because interestingly, there is a bit of the difference between how we do it in the GPU and how it's done in the real time, and some stuff is a bit less obvious. So we utilize hardware texture sampling whenever it's possible. Of course, on CPU, there is nothing that helps us, so we need to re-implement the sampling. But the compute backends like CUDA or OneAPI or HIP do support bilinear texture lookup optimized by the hardware. It's basically similar to your more traditional real-time engine shaders. And the tricks we do to support bicubic filtering on a GPU and probably on a CPU as well is we boil it down to 4 bilinear lookups and then do smart tricks with the weights. So all this kind of adds the restriction to your tile cache implementation, which currently is work in progress in a branch, which means like, okay, so you need to pad the tiles with extra pixels around, which kind of diverges a little bit from more traditional TX format used by the VFX people. And for the 3D volumes, we actually use NanoVDB library, which is a header-only implementation of algorithm which basically interprets reads the open VDB grids. There are a couple of tricks we do to speed up the filtering, especially for 3D case. So because like it's explained in more details in the paper, which you can see on the slide. The basic idea is that, okay, we do the Monte Carlo sampling where we might be sampling the same texture from in a similar position for multiple AA samples. You can assign some weights to it, and by smartly assigning those weights, you can mimic the way how the bilinear lookup or bicubic lookup would look like. So for example, with properly assigned weights or like choosing which of the pixel to sample, you can replace the bilinear lookup by choosing properly the nearest pixel, like one or another. And I show the sample, it chooses like either one pixel or another pixel. We don't do the interpolation for each of the sampling. And similarly, you can do the bicubic lookup, where you can break down the bicubic sampling into the either multiple bilinear lookups or multiple nearest lookups. And this approach works on the CPU and GPU, and you can use it for 2D or 3D cases. Currently in Cycles, we implement this approach for 3D case, just because that's the main bottleneck which we run into, especially with the nano-VDB approach, where you don't want to be sampling, like when you sample on the boundary of a grid, then like it ends up in a huge amount of the memory throughput you need to do. So using the stochastic rendering, stochastic sampling helps a lot in the memory bandwidth. There is a bit of limitation when this approach can be used. So for example, if artists in their shader use some nonlinear operation on the result of the sampling of the, for example, density grid, for example, they added ramp node to make things more interesting looking on the screen. This approach doesn't work because it's nonlinear operation. And for those cases, we roll back to more naive and more slower classical bilinear and bicubic interpolations. And the last section I wanted to talk about is the interactive viewport, because again, we value a lot the interactivity of Cycles. That helps a lot with the artistic workflow. And the way we do it is we utilize dynamic BVH. I think it was covered yesterday in one of the talks that basically we have top-level acceleration structure and bottom-level acceleration structure, and the top level only points to the bottom-level acceleration structures. Well, for the final renders, we can allow having some geometry in the top-level structure just to optimize the array queries when there's multiple overlapping objects. So in the viewport, we use dynamic BVH, which makes it quite easy and cheap to update the optimization structure when someone moves face or moves vertex or moves an object. So it kind of like leads to the lower quality BVH, but faster update rates. We also utilize the idea of progressively dropping resolution. So for example, we just start rendering, and when you navigate the camera, we will drop resolution to lower value, and then once the navigation finished, we will start increasing the resolution up to the final. We also utilize the knowledge that there are retina screens, for example, and it doesn't really make a lot of sense in a lot of cases to render the actual physical pixels. Artists don't usually see the difference, and that saves a lot of time in rendering in the viewport. And we're also currently looking into technologies for the temporal denoising and upscaling in the viewport. It's currently work in progress. There is no promise we can currently make, but that's something that is interesting, and we're looking into it. And for the future, there is, ever since us switching to the wavefront rendering, there was this idea that, hey, we can stop wavefront at any moment we want. So what we can do is during navigation to only do the primary bounds and then do the viewport update. So in the complex scenarios, people will see not final lighting, but they will have enough information on the screen to help them navigating the camera. And additionally, all the scheduling in both viewport and actually for final renders as well, we base scheduling on the statistics we gather during rendering. So for example, we gather timing performance of the path tracing step and the denoising step, and we also keep track of the GPU thread utilization. For us, that means that, okay, so how many threads were busy, how many threads were idling, and basic idea is like to calculate number of samples to render in one batch to keep interactivity. So if we know that, hey, samples render quite quickly, so we can schedule more samples at once. If we know that GPU was mostly idling, we can add work to do without affecting render time as well, and then people in one redraw will have less noisy results. And currently we're trying to target 12 FPS in the viewport, but we also have some clamping in place, so cycles cannot drop down the resolution too much, or cannot, well, it cannot render less than one sample. And with that, there are some references which were linked in the slides before, and that's all I have for you today. So thanks for coming. I don't know if you have some time for questions or.
Just hi, yeah. So the wavefront scheduling has quite some logic in it, which seems not very parallelizable. So this makes me assume that the scheduling is done on the CPU, but then I figure the CPU instructs the GPU to run a kernel, and it awaits it, and this sort of creates a bottleneck in GPU usage or occupancy. So how did you tackle that problem?
So that's a great question. So there are like a few things which we do. Like sometimes there is no dependency between kernels, so you can just schedule multiple kernels at once and only then do synchronization, and kind of leave it to the driver to do the most efficient thing it can do. The other thing we wanted to implement is the GPU side kernel scheduling, but unfortunately it is not supported in all the GPUs we want to support.
Hi, thanks for the presentation.
Oh.
So you mentioned the shader virtual machine and the execution of the shader code. Has that been a sort of performance issue at some point, or because it's not really, it cannot be fully optimized by like the specific implementations, for example, with, for example, the hardware ray tracing, or have there been any ideas relative to that, or is the performance already really good that it's negligible?
So was it a problem before? Yeah, it was a problem because compilers, like, in the early days of cycles, we were quite early adopters of all this technology. So for a long time, compilers were doing wrong decisions about register spills, and they're inlining much more. So that was a problem. Now it's less of a problem. If you use some ray tracing functionality from the shader, then it kind of becomes a problem again, because for hardware ray tracing call, it can only happen from the direct callable, so I think everything needs to be inlined as well. So there's, of course, some improvements we can do. Whether performance is good enough, so far it was good enough. The next step would be probably to implement the actual specialized shader, but like stick to like two-stage optimization, where like while change happened, we use the SVM approach, and then schedule some kernels to be compiled in the background and kind of like transparently switch them around. So that's the idea we plan to explore.
So when did the SVM thing, the shader virtual machine, get conceptualized and started working on? Like, can you give it like a time frame?
So it was like from the very first days with cycles, and like I think it was released in 2011, and that was what we originally shipped with.
And do you have separate instruction streams for separate things like importance sampling and then the evaluation of the estimator, or is it all one stream?
It's just like one stream. Well, the opcodes are quite like high level, actually. So for example, if you need to do like BSD, it's like for principle, it will be one opcode. If you want to do texture noise sampling, it will behave on like Gabor noise or something. So they're quite high level.
Thanks for the talk. So if I understand correctly, from the CPU, like when you use the CPU backend, you have array, you trace array, you hit some surface, you run the material shader through this SVM thing. And I'm assuming most of this is the mix of scalar and vector-3 math. If that's true, do you get advantage by using AVX at all? Because you mentioned it in the slides, but it's not like clear where it helps.
Yeah, so the challenge with all of that is, again, becomes the thread coherency. So maybe on the CPU, the most efficient approach will be kind of like a mixture. So you do the wide SMID for shading, and you do wide SMID for ray trace. So then you can have like enough load for all the elements on the CPU to run. But The rest is like you probably wanted to roll back to a more Scala approach.
Right, but right now you don't do this, right?
Currently we don't do it. We did like some early investigation with the Imbre trying to see, okay, how much faster things can be, and the numbers were like not very compelling for us to invest like time at that moment. We had like something more important to tackle, but now it's like we'll need to come back to it and revisit and see where we are now.
Thank you.
Hey, so you mentioned that you ship precompiled kernel binaries for most backends except for Metal. So I was curious, what exactly was the challenge with shipping like precompiled Metal libs? Why does that not happen?
Like for the challenge of shipping precompiled on Metal or like on other platforms?
Yeah, so Metal.
Metal doesn't provide the ability for that like at all. Like with CUDA and one app, you can say, hey, give me this binary. Metal really forces you to do just-in-time compilation optimization just because they believe that it will give the most optimal thing as far as...
Okay, let's talk after this.
The what?
Let's talk after this.
Okay.
Hi, thanks for the talk. So you mentioned that you have like for device backend like CUDA, optics, HipRT, and it's clear that perhaps because it's better performance for each platform. But for example, if you switch to Vulkan compute, Vulkan hardware ray tracing, benefits of it like you have to support let's 1 IP instead of 3 or 4. Is Vulkan would be that slow, so it's worth using this all CUDA, HipRT, etc.?
I mean, that's a good question. We've been kept asked that question a lot, and like partially problem is that the compiler state of the Vulkan is not. We believe it's not there yet to handle complexity of even these microkernels. And another thing is integration with the rest of the feature set. For example, for the Metal, like what do you do on Apple devices to do hardware ray trace, or what do you do with the shader compute? So you still need something.
So you've shown the like the shader node virtual machine, and in the example you had like a stack at the bottom. I wanted to ask, like, usually when you compile a shader, I'm expecting it, like, especially on like at least on the AMD platform, you need to know ahead of time how many registers you're going to use in the shader. But it seems like the stack is going to be unbounded, at least the way you presented it, because it could always like append another node to it. So how do you handle that? And
so we have a fixed stack of like 256 floats. And most of the shader fits into this limitation, but you can create arbitrary complex things with like, links going from somewhere far on the left to the far on the right, and then you will run out of space. But in practice, it's not a huge problem for artists.
Hi. Can you elaborate on the strategy? What happens if the virtual machine wants to sample a texture and it's not resident yet in the texture cache? Like, what happens on the GPU? You just stop?
So that's a fantastic question. That's something we're currently working on. So basically the idea is that, okay, so you try to sample something, it's not there, then you record, hey, we needed this texture, we needed this tile, we stop execution of the shader, and on the CPU we do read back saying, okay, so those tiles were missing, and then we upload them to the GPU and resume the shader execution.
Thanks for the talk. One question on the sickle. So HIP, you use HipRT. So what's the plan for sickle? You expect people to do sickle with sickle ray tracing exposure?
So currently the sickle is implemented for Intel GPUs. It's a great question. How would hardware ray tracing integrate into there? Maybe it could be implemented as part of the Imbre library as well, like similar to...
I'm actually more interested in not Intel, but Qualcomm. What's your plan on Qualcomm sickle integration?
So for the Qualcomm, we are in contact with them, and then we're trying to push them, or like saying, hey, we would really prefer if it's done as part of one API somehow, and we were trying to make them talk with Intel, but then at some point the communication stopped, and I'm not sure what's going on there. From our perspective, it seems to be like possible that okay, so if something works for Intel GPUs, and if Intel is open for external contributions as well, like why not to integrate into the library we already use?
Thank you.
That kind of will be preferred for us anyway. We can see the point from other vendors, but like for us, it will be so much easier if we don't add more backends and libraries.
Can I ask everybody in the back to be a little bit more quiet?
Yeah, so you mentioned that the Megakernel approach is specifically important for getting down shader compile times. I'm wondering, how do you compile your shader VM? So this big switch loop, is it also problematic to compile? And if so, how do you deal with that in a daily work environment where you need to compile this VM probably with every change you do?
The SVM compilation takes like, it goes quite fast. There is like no like huge amount of complicated logic going on there. Like it doesn't try to be smart. It doesn't try to do the typical things that compilers will do to optimize things. It kind of like trades the optimal performance with the interactivity. And for artists, it was very important that interactive part is there.
All right. Thank you, Sergey.